Okay. So welcome to Math 150, Lecture 31, Triple Integrals. So what I want to do today is talk a little bit about how do we do triple integrals. In a shaka, it's basically going to be the same as double integrals, which is for the most part the same as single integrals. You just keep doing what you know. The difficulty is setting up the bounds of integration. So for a lot of regions, if it's rectangular, it's really nice because if it's a rectangular region, the bounds for each are independent of the others. We saw when we looked at integrating over a circle, if we fixed x, that then changed the range for y. We saw this for other regions where we had the left and the right curves or the lower and the upper curves. And so most of the difficulty in multivariable integration is just finding how do you write down the region you're integrating over. There are certain regions that initially do not look like rectangles, but with a change of coordinates become rectangles. Can somebody give me an example? Circle. So if you change a circle to polar coordinates, it becomes a rectangle. The unit circle is now 2 pi by 1. A cylinder becomes a rectangle when you change coordinates. A sphere becomes a box. I'm sorry, not a cylinder becomes a box. A sphere becomes a box when you change coordinates. This is why we do stuff like this. It makes things a lot nicer. So, you've got 3 homework problems for the next class. For a lot of them, we want to find, the region bounded by, and we'll give you something that gives you the region in the XY plane, and then the height will be Z. So there's, a couple of different ways to doing this. If I have some function Z, which depends on X and Y, I can view that as my height. And I just integrate the function f of xy over my region in the xy plane, and that will give me the volume. The other thing I can do is I can have my region viewed as a 3-dimensional region in x and y and z, and I integrate the function 1. So for example, let's say I give you f of xy is the square root of 1 minus x squared minus y squared. And I'll do this for, say, 0 less than equal to x squared plus y squared less than equal to 1. So what kind of region would this be? Almost. Well, if I think about what's going on, so let's try to draw this 3-dimensionally. Here's my x-axis, my y-axis, and my z-axis. If I look at what's going on here, so my base is going to be a circle, but now if I go up to the square root of 1 minus x squared minus y squared, what kind of region will I get? It'll be a dome, but it's a very special dome. If z is equal to f of xy, so z is the square root of 1 minus x squared minus y squared. Whenever you see a square root, what's your first instinct? So when you see a square root, what's your first instinct? I'm sorry? You've got a square root. What can you do to make things nicer to both sides? Square. So if you square both sides, you get z squared equals 1 minus x squared minus y squared. How could we rewrite that? I'm sorry? Yeah, so this is just x squared plus y squared plus z squared equals 1. This is a sphere. Or maybe a hemisphere. Because, I'm taking the positive square root. So if I look at what's going on, what I really have is I have, a sphere coming up over the xy plane. And so if I want to try to figure out what's going on, I could integrate over 0 less than equal to x squared plus y squared less than equal to 1 of f of xy dA. That would give me the region. Or I could also integrate over 0 less than equal to x squared plus y squared plus z squared less than equal to 1, z greater than equal to 0 of 1 dv. And both of them are going to give the same quantity. If you think about it, what's happening in the first one is I pick a place in the xy plane and I go all the way up to the top of my surface. Well, if I write the other integral really explicitly, let's say x goes from -1 to 1, y is going to go from negative square root of 1 minus x squared to the square root of 1 minus x squared. Z is going to go from 0 to the square root of 1 minus x squared minus y squared, 1 dz, dy, dx. And that's what I'm going to have in the second one when I'm integrating the function 1 over my region. X goes from -1 to 1. Once you choose what x is, that restricts a little bit what y is. And then z goes from 0 until I hit the top of the hemisphere. Well, the first integral isn't that bad to do. What's the integral of 1 from 0 to the square root of 1 minus x squared minus y squared? Yeah, it's just the square root of 1 minus x squared minus y squared. So this would just be equal to the integral x goes from -1 to 1, integral y goes from minus square root of 1 minus x squared to the square root of 1 minus x squared of the square root of 1 minus x squared minus y squared dy dx. This is just the integral over the region 0 less than equal to x squared plus y squared less than equal to 1, f of x, y, dA. It's exactly what we had before. So there's two different ways to view some of these integrals. If I want to calculate a volume, if I'm integrating from the bottom curve to the top, that's just giving you the change in z. And so rather than doing it as a triple integral, why not just do it as a double integral? Because if you think about it, what's the triple integral that we're doing? We're just integrating the function 1 from the lower value to the upper value. Well, okay, if we're just integrating 1 from the lower value to the upper value, we're just essentially finding the height. This is very similar to what we did for areas under the curves. If I give you two curves in the plane, so let's say here is g of x, and here is, say, f of x. Maybe here's A, here's B. And then for each of these points, if I want to find the area of the region, there's two different ways I can do this. I can find the area. It's going to be the integral x goes from A to B of f of x minus g of x dx. And it also equals the integral over, let's call this region R, over all pairs x, y, and R of the function 1 dA. And the way I've drawn this is this simple. Well, simple means it's got to be x simple and y simple. So for this one, if I try to integrate from if I fix a value of y, there are times I enter the region, leave it, enter again, leave the region. So it's not simple if I fix y, but it is simple if I fix x. And so the way we would evaluate this integral is we would do it as an iterated series of integrals. And so we would then do it as the integral x goes from A to B, the integral y goes from g of x to f of x of 1 dy dx. And that's just going to be exactly what we had a moment ago, the integral from A to B of f of x minus g of x dx. So when we extend things to 3 dimensions, it's really what you've already seen in 1 dimension. It all comes down to what's the easiest way to do the computations. Right now, we don't have that many techniques to handle integration in several variables. We have switching the order of integration, and depending on the region I give you, sometimes one is going to be better than the other. And then the big thing that we're going to lead up to is we want to try to find ways to change variables. So that's going to make regions look nicer. Okay. So let's talk a little bit about some change of variables. So who remembers polar coordinates? You know, what do x and y equal in terms of r and theta? R cosine theta, good. So r cosine theta, r sine theta. If we go in the other direction, r is the square root of x squared plus y squared, and theta is arctangent of y over x. If I wanted to draw the little picture, you know, this would be theta, this would be r, this would be the point xy. And so we have a way to pass from one to the other. What we want to do is we want to figure out how do we pass from the area element dx dy to the area element dr d theta. And the idea is that there is some function that we can put here. We don't know what it is yet. That will tell us how an infinitesimal area element dx dy changes into our theta space. Now, unfortunately, that change might depend on where we are. So depending on your value of r and theta, you might have a different weight. If we have simple change variables, that's not going to be the case, but it will be the case in general. So let's try to think about what's going on. I will risk writing down a formula that almost surely you have either not seen in calculus or you've seen and you forgot. Who remembers the formula to find the area of polar integration? So I will risk writing recall if given r of theta, then the area is the integral theta goes from theta 1 to theta 2 of 1/2 of theta squared d theta. Has anybody seen this formula? So for instance, you know, if I give you a curve, you know, that looks, say, something like this, and here's my r equals r of theta, I want to figure out what is the area of this region. And if you think about what's going on, I can break this up into lots of little infinitesimal triangles. So I'll zoom in on one of those triangles. So here's the angle theta. Here's r of theta. Here's r of theta plus delta theta. And then this arc length over here is going to be r delta theta. What's the area of a triangle? One-half base times height. So the height is approximately r of theta. The base is approximately r delta theta. And so the area of each of these little triangles is going to be approximately 1/2 r of theta times, r of theta times r of theta delta theta. And that's where the formula 1/2 r of theta squared d theta comes from. If you haven't seen it, don't worry. But just in case some of you have seen it, it's probably not proven rigorously in a Calc 2 class. Just wanted to quickly state where it's coming from. The key idea here is that if we want to talk about arc length, the length of that arc is not delta theta, it's the radius times delta theta. Well, that makes sense. If I go, 90 degrees, how far have I traveled? Well, it depends. Am I walking on a circle of radius 1, radius 10, radius 100, radius 1,000? The larger the radius, the more I've traveled. So the arc length, it's going to not just be delta theta, it's going to be r times delta theta. So let's look a little bit more closely at polar. So imagine I have a circle of radius r, and I'm going to increase the radius a little bit. So let's say maybe this is r plus delta r, and I'll have a slightly smaller circle of radius r. and I have some angle theta, and I increase it by delta theta. And I can ask, what is the area of that little segment? So any thoughts as to how I would find the area of that segment? Good, so it's the area of the outside minus the area of the inside. So, so it would be pi r plus delta r squared minus pi r squared. That'd be the area of the big circle minus the area of the smaller circle. But then what fraction of this do I have? Delta theta over 2 pi. And as a quick check, if delta theta equals 2 pi, I have the whole thing. If delta theta is 0, I have nothing. If delta theta equals pi, I have half. So that's going to be the area of that little segment. Well, we can expand things out. We'll get to be pi r squared plus pi, 2 pi r delta r plus pi delta r squared minus pi r squared times delta theta over 2 pi. So the pi r squared cancels with the negative pi r squared, 2 pi cancels with the 2 pi. So we get r delta theta plus 1/2 delta r squared delta theta. So that's going to be the area of that small little bit. What do you notice is different between the two terms? What's the biggest difference between the two terms? Okay. So be more specific. How many small factors does this have? The second term has how many small factors? So you said it has a delta r squared. That's correct. That's the first half. How many small factors does delta r squared delta theta have? What if I write it as the first is r delta theta, the second is 1/2 delta r delta theta. How many small factors does this have? So this has 3 infinitesimal factors, and this is just 2 factors. So if you think about what's going on, we're going to chop up the radius and then we're going to sum over the different pieces. We're going to chop up the angle and sum over all the pieces. We have 2 sums. So what we saw before when we did the proof of the fundamental theorem of calculus, we had the delta x, and delta x was really small. Delta x was of size 1/n. If you multiply something by 1/n as n goes to infinity, that's going to 0. But we had a sum from 0 to n. And so even though each piece was multiplied by 1/n, because we had n pieces, it could actually give us a contribution at the end of the day. And so it's okay to have something tremendously small if you have a huge number of them. You can still get a contribution. If I'm chopping up the radius and I'm chopping up the angle, I'm going to get a sum over the radius. I'm going to get a sum over the angles. So if each one of these is of size 1/n and I have 2 sums where each sum has n terms, how many terms will I have total if each one has n terms? So my first sum has n terms, my second sum has n terms. So if I look at the double sum, how many terms will there be? I'm sorry? Not 2n. So I'm going to have, let's say a sum, n goes from 0 to n minus 1. Let's say a sum, we'll do 2 variables. We'll do m goes from 0 to n minus 1 of 1. And then we'll say 1/n, 1/m. how many terms are there? If n goes from 0 to n minus 1 and m goes from 0 to n, let's make this. Let's make this I goes from 0 to n minus 1. Let's make this j goes from 0 to minus 1. So the first term, I goes from 0 to n minus 1. How many pieces do we have in the first term? N. And in the second, we have m terms. So for each choice of I, how many choices of j are there? M, right? When I equals 0, there are m summons. When I equals 1, there's m summons. When I equals 2, there's m summons. So how many summons are there total? N times n. So this has n times m summons. So even though I'm multiplying by the really small 1 over n times m, I have a huge number of pieces. So the sum can actually be a nice, reasonable, finite number. If I look at what's going on over here, if I sum over the delta r's and the delta thetas, if this is of size 1 over n and this is of size 1 over m, I'm going to have an extra small delta r. So this will not contribute, doesn't contribute in the limit. It's like, a sum I goes from 0 to n minus 1, sum j goes from 0 to m minus 1, our function, and then the delta r, call that 1 over n, call the next one 1 over n, and call the theta something like 1 over m. If you want, we can do, capital R, 2 pi for just, how big they are. But when you look at it like this, you see that this term is not going to contribute in the limit. We have too many small things. We're doing an area integral, but we have 3 infinitesimals. We can only have 2 infinitesimals for an area integral. Just like in one variable calculus, when we did a line integral, all that matters was the delta x. So over here, because we have a delta r, delta theta, this term is much smaller than this term. If you want, another way of looking at it is, if I just drop this delta r, the 2 terms are going to be similar in their infinitesimals, correct? So imagine delta r is 1 over a billion. Then the contribution of this should be 1 billionth of the other. Now make delta r 1 over a billion squared. Then this should be 1 over a billion squared of the first. Then make it 1 over a billion cubed. It should be 1 over a billion cubed of the first. So because we have an extra delta r, we don't expect this to matter. So in the limit, this is the only thing that contributes. This is what matters in the limit. So what we're really seeing is this little area segment is becoming r dr d theta. So we get our polar conversion factor. dx dy goes to r dr d theta, which you really should view as dr times r d theta. If you write it like that, then you have length times length. Well, we normally put the items we're integrating over next to each other. Let's check and see if this is reasonable. Can somebody give me a region that looks really nice in spherical, in polar coordinates, whose area we know? So what would be a region that looks nice in polar coordinates? Circle, right? It's the only thing we can try. So if we look at a circle, the x integration is the integral x goes from minus, do you want to do a radius of 1 or a radius of capital R? 1. X goes from -1 to 1. Y goes from minus square root of 1 minus x squared to the square root of 1 minus x squared, 1 dx dy. And now this becomes the integral, and my function is still going to be 1. And then dx dy becomes r dr d theta. So I have to specify the r bounds first. R goes from 0 to 1. Theta goes from 0 to 2 pi. Okay, what does the r integration equal? So I can actually split this as two integrals, d theta times the integral r goes from 0 to 1 of r dr. Because the theta and the r integrals don't impact each other. So what's the integral of d theta from 0 to 2 pi? Two pi. And what's the integral of r from 0 to 1? Not 1. What function has derivative r? 1/2 r squared. Right. So it's going to be r squared over 2 evaluated 0 and 1. So you get 1/2. So you get 2 pi over 1/2. So you get pi. We do get the area of the circle. And if I did a radius capital R, I would get that. If I tried to do this integral, I would get the integral x goes from -1 to 1 of twice the square root of 1 minus x squared dx. Or noting that it's an even function, this would just be 4 times the integral from 0 to 1 of the square root of 1 minus x squared dx. We can evaluate this if we do some trig substitution. Okay. Again, we have to be very careful. Have we actually proved the area of a circle, or are we using the area of a circle to now do some calculations? Where do some of these results come from? Well, if you think about it, where did we get the r dr d theta from? We came from looking at the area of a big circle of radius r plus delta r minus the area of a circle of radius r. So we used the fact that we knew the area of a circle when we were trying to answer this. So again, you've got to be very careful about what are we using. But this at least shows that things are consistent. It gave the right answer for the area of a circle. There is occasionally a third technique of multivariable integration. So I've talked about switching orders of integration. I've talked about changing variables. Another technique of multivariable integration, and this is really hard to use, is to take a one-dimensional integral and convert it to a higher dimensional problem. This is the exact opposite of what you normally do in life. Normally what you do in life is you take a complicated problem and you reduce it to a bunch of simpler problems. I would much rather do a lot of simple problems than one hard problem. So here is one of the most important integrals in all of mathematics. The Gaussian integral. And so I'm going to do a normal with mean 0 and standard deviation 1. So out of curiosity, how many of you have seen the normal Bell Gaussian? How many of you have seen this in a stats class or something? A good number of you. So let's let I be the integral from -infinity to infinity of e to the negative x squared over 2 dx. I want to figure out what is the normalization constant to make this a probability distribution. And we talked about how we don't have a nice closed form antiderivative for this. And we talked about how we could come up with an infinite series expansion because we know what the integral is, not from -infinity to infinity, but -infinity to where? 0. It's going to be half the total. And so we were able to use that to get some kind of series expansion. We can play some games and whatnot. But how do we know what the normalization constant is? How do we know what to put in? We know half the integral comes up to 0, but how do we know what that value is? It's a beautiful trick. Do you agree that I squared is the integral from -infinity to infinity, e to the negative x squared over 2 dx integral? And I'll write this x goes from -infinity, y goes from -infinity to infinity, e to the minus y squared over 2 dy. Is that true? What have I done? So why is this true? Yeah, the two integrals are the same. I'm just using a different dummy variable. Could I have used Q as my dummy variable? Could I have used a smiley face? Yes. I can use a smiley face as a dummy variable. I would look silly, and my mathematical colleagues would make fun of me. How many of you have ever played games of cards? What are the suits? Yeah, so we always say spades, hearts, diamonds, clubs. That's the canonical order, but yes. Could I play instead with cauliflower, cucumbers, kumquats, and chicken? Yes. Should it make any difference if I change and now have pictures of carrots rather than clubs? Would it make any difference as we play the cards? No, although they've done psychological studies as to whether or not this impacts people's ability. And I think the experts can make the change without any trouble, but novices are thrown by the different colors and the different shapes. But it makes no difference what you choose to use. We can't use X because X is really being used here, so it would be bad notation to use the same letter. Well, this is the same as a double integral. X goes from minus infinity to infinity, Y goes from minus infinity to infinity, e to the negative x squared plus y squared over 2 dy dx. So if you think about what we're doing, we're integrating over all of space. So let's convert to polar coordinates. So I have my function f of xy is e to the negative x squared plus y squared over 2. F of r cosine theta. Actually, this is something I'm trying to do fast. So f of r cosine theta, r sine theta, what would that equal? So when I'm changing my integration, I have to change the bounds of integration, and I have to now have my function a function of just r and theta. Right. So what would you get when you now look at x e to the x squared plus y squared? Okay. 2. So this integral is just going to be the integral e to the negative r squared over 2 r dr d theta. We're integrating over all of space. So theta goes from 0 to infinity. Theta goes from 0 to 2 pi. So this is the integral theta goes from 0 to 2 pi of d theta times the integral r goes from 0 to infinity e to the negative r squared r dr. The theta integral is just going to give me 2 pi. What function has derivative e to the negative r squared times r? So what would have derivative e to the negative r squared? Almost, you are extremely close. It's a negative. You could do a u substitution. You know, let u equal r squared, then du is going to be minus 2r dr. So actually, it's not just negative e to the negative r squared. It's negative 1/2 of that, right? So negative 1 over 2, and then we evaluate this at 0 and infinity. So we just get that this is equal to pi. So again, do the u substitution if you're not comfortable. Do u substitution where u equals r squared. Du is going to be minus 2r dr. So r dr would be minus 1/2 du. And so if I squared equals pi, what does I equal? So if I squared is pi, oh, I'm sorry. Make a mistake. Oh, no. There's no factor of 2 because, I'm sorry. Did you say e to the minus r squared or minus r squared over 2?
It's not over 2.
I'm sorry, it is over 2. I think I dropped the 2, I think, when you said it. So it's just negative 1, my fault. The 2 we have in the denominator is actually designed beautifully for the change of variables. And so when everything comes out nicely, we're going to just get e to the negative r squared with a negative sign. And that's over 2. Okay, so we get I squared is 2 pi. So if I squared is 2 pi, what does I equal? Yes. Is there anything else it could be? You're correct. So why do we know it's not the negative? We just know I squared is 2 pi. So why is it not negative square root of 2 pi? No, negative square root of 2 pi is a real number. You are correct that it is the square root of 2 pi, but why is it not negative square root of 2 pi? You can if the function's below the x-axis. Look at what we're integrating. We're integrating e to the minus x squared over 2 from negative infinity to infinity. What can you tell me about the integrand? What can you tell me about the function e to the negative x squared over 2? Is this function ever 0? Is this function ever negative? This function's always positive. So that means I has to be greater than 0. So as I is greater than 0, we take the positive root. So this is one application of polar integration. We can actually use this to evaluate the Gaussian integral. This is one of the most important integrals in all of probability, in all of mathematics. It's what allows us to come up with the normalization constant of the standard normal. And if you then do some change of variables, you can then figure it out in general. As a nice exercise, for fun, integrate from minus infinity to infinity 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx. Show this equals 1. You can do this by just changing variables. And so it's just good practice to make sure that you can do the change of variables. This is mathematics at its best. You reduce as many problems as you can to something simpler. If we can handle the case of the Gaussian with the mean 0 and standard deviation 1, we can then handle the general case of mean mu and standard deviation sigma. Yes? Yeah, yep, because it's clearly non-negative. And so the other condition we need for it to be a density is that it integrates to 1. And so we did the special case when mu is 0, sigma equals 1. So in that case, we know the answer. What I want you to do is just show by changing variables that this is the same as now solving that this equals 1. And again, this is just a good way to check and make sure that you're comfortable with your integration. Most of the multivariable integration you need to do, the multivariable part is setting things up. You have to be comfortable with your Calc 2. So if you're not comfortable with your Calc 2, remember I gave you all those review problems at the beginning of the semester. The TAs are available, I'm available. Go through and do the details of this problem. Do the U substitution. Make sure you're able to do this and get all this to work out. Okay, this is the type of stuff we need to be able to do. Okay, so let's try to calculate the volume of a sphere. So when you think of a sphere, what natural coordinate system to think of? Spherical. But we could actually do this with polar. And if we're going to do it with polar, we would want to then integrate over a circle. And so this is the same as integrating x goes from, do we still want to do the radius as 1 or do we want to do the radius as capital R? 1. And again, if you can solve it with the radius of 1, you just argue if I rescale by a factor of r, then area is going to be proportional to r squared, volume is going to be proportional to r cubed. So if I can get the area when r equals 1, I just multiply by r squared. In general, if I can get the volume when r equals 1, I just multiply by r cubed. All right, so x goes from -1 to 1. Y goes from negative square root of 1 minus x squared to the square root of 1 minus x squared. And then the square root of 1 minus x squared minus y squared dy dx. So here, f of xy is the square root of 1 minus x squared minus y squared. Do you want to calculate the volume of a sphere or a hemisphere? What do people want to do, sphere or hemisphere? Sphere. So I should multiply this by what? So if I multiply by 2, I now get the volume of a sphere. So this is the volume of a unit sphere. So f of xy is 2 times the square root. What would f of r cosine theta r sine theta be? So I need to replace x with r cosine theta. I need to replace y with r sine theta. And if you want, a nice way to view this is just 2 times the square root of 1 minus x squared plus y squared. So what would this become? Yep, perfect. And so for a lot of these problems, there's really no theta dependence. And that's one of the nice things is if you have a system that has no theta dependence, the theta integral often becomes nice. You can split the integration. So now we have the double integral. We have our function is 2 square root of 1 minus r squared. Dx dy becomes r dr d theta. R goes from 0 to 1. Theta goes from 0 to 2 pi. I've hopefully done this enough times that you can see that this breaks into 2 integrals, the r integral, the theta integral. What does the theta integral equal? It's just 2 pi. You can write it as we've written before. What we did every previous time was, I broke it up. Here's my theta integral. Here's my r integral. Because my function splits as a function of theta and a function of r, and the bounds don't depend on each other, I can write it like this. If I had a horrible function, if I was integrating e to the minus r cosine theta, I can't split it up like this. If my bounds on r depended on theta, I can't split it up like this. But because my theta goes from 0 to 2 pi, my r goes from 0 to infinity, my bounds are independent of each other. And because my function splits us to a function of theta 1 times the function of r, I can break it up like this. If you're not comfortable doing this, by all means, do the extra step. But my theta integral is just going to become 2 pi. So this is just going to be 2 pi. The integral r goes from 0 to 1. I've got a 2 coming out as well. And I've got the, well, I'll keep the 2. I've got the square root of 1 minus r squared 2r dr. We live well. This is screaming at you to do something. What is it screaming at you to do? U substitution. What should we take u to equal? 1 minus r squared. So if r goes from 0 to 1, then u goes from where to where? One to 0. I always like being extremely explicit and writing down before I do anything, what's my u, what's my initial bounds of integration, what's my new bounds of integration. So du is negative 2r dr. So 2r dr is equal to negative 1/2 du. No, I'm sorry, it's just equal to negative du. So our integral is going to be 2 pi. The integral u goes from 1 to 0. We now get u to the 1/2 and then -1 du. Yes. Does everyone agree that the negative sign just flips the order of integration? So this is then just going to be 2 pi integral u goes from 0 to 1, u to the 1/2 du. I like having my integration go from small to large. I would much rather just use the minus sign right now and fix that. All right, what function has derivative u to the 1/2? So let's first figure out what's the exponent of u. If I want to get down to u to the 1/2, what should the power of u be? 3/2. So I want a u to the 3/2, but when I take the derivative, I'm going to get a 3/2 coming down. So I either multiply by 2/3 or I divide by 3/2. I'll just divide by 3/2. This is how I think about it in my mind. I'm increasing the power of u by 1. It's going to bring down to 3/2. So if I divide by 3/2, that will cancel. I now evaluate this at 0 and 1. Okay, well, what I get at 0 is going to vanish. What I get at 1 is just going to be 1. So I get 2 pi over 3/2. So this is equal to 4/3 pi. All right, that is the formula for the volume of a unit sphere. So we were able to get this by doing the integration. Is the integral of the square root of 1 minus r squared painful? A little bit, but we don't have the square root of 1 minus r squared. We have the square root of 1 minus r squared times the 2r dr. When my kids were young, people would sometimes ask me, which kid did I love more? And it was always very easy. It's whoever slept better the night before, that put them into first place. Now that they're older, much different. Over here, I have two things in front of the dr, the 2 and the r. Which do you love more for this problem? Which is more beneficial to you, the 2 or the r? The r, right? Because of the r, I can do a u substitution and everything works out nicely. So when you're doing problems like this, there's only certain integrals that we will be able to do in a nice closed form. And it's, what's responsible for the miracle? If I try to do something like this in Cartesian, it's much worse. So we've got about 2 minutes left. Let's go back to the area of a circle. So area of a circle. So we have the integral x goes from 0 to 1. Then we had the integral, let's see. We had the square root of 1 minus x squared, and I think we had a factor of 4 dx. And that would be the area of the circle. So we need to figure out how to do this integral. Does anybody remember how to do these integrals? What kind of substitution you do? Is it what? So this is, it's either going to be sine or cosine. I think we want to do sine because when x is 0, I'd rather have. So if we try x is equal to sine theta, then as x goes from 0 to 1, theta goes from 0 to pi halves. And then we would get this is equal to 4 integral theta goes from 0 to pi halves, the square root of 1 minus sine squared theta, then dx, derivative of sine is going to be cosine of theta d theta. Yes. And so we're going to get 4 times the integral theta goes from 0 to pi halves. What's the square root of 1 minus sine squared? 1 minus sine squared is cosine squared. Square root of that is cosine. So we get cosine squared theta d theta. Now, if you happen to remember cosine of theta halves plus theta halves, no, sorry. The cosine of theta plus theta is cosine squared theta minus sine squared theta. So the cosine of 2 theta is going to be 2 cosine squared theta minus 1. So cosine squared of theta is going to be 1/2 cosine 2 theta plus 1. So you could use that to do this integration. You could also note that this is 1/2 the integral from theta goes from 0 to pi halves of cosine squared theta plus sine squared theta. I'm sorry, which is just 1. So you would get 2 times the integral theta goes from 0 to pi halves of 1 d theta, which is 2 times pi halves, which is pi, which is the area of a circle. So you can either use this beautiful trick of relating the integral of cosine squared to the integral of sine squared, or you can try to remember your trig identities to figure out. But we have to do a lot more work to make this integral work. All right, so this is a good place to start. We will continue with changes of variables in the next class.